All right, AUB students, welcome to the Explainer. If that Phys 210 final is on your mind, well, you've come to the right place.
Look, we get it. The pressure is definitely on. You've gone through a ton of material this semester, right? From waves to thermo, and now it's crunch time. Time to connect all those pieces for the exam. So just think of this as your super fast guide to the big ideas. We're not here to just throw formulas at you. We're going to lock in the intuition behind the key principles that you absolutely have to know. We're going to kick things off with the essentials of waves and sound. Then we'll see how those exact same concepts apply to light and physical optics. After that, a really quick but super important review of fluids and thermo, and then we'll wrap it all up with the final takeaways. So let's jump right in. Okay, first up, waves and sound. Seriously, this stuff is the bedrock for so much of the course, so making sure we're solid here is key. Let's start with the most fundamental piece, the wavefront. Just picture dropping a rock into a still pond. A wavefront is just one of those perfect circular ripples expanding outward. Every single point on that ripple is doing the exact same thing at the exact same time. That's it. That's the core idea of how waves move. Now, what's really important here is what controls a wave's speed on, say, a guitar string. It's all about the string itself. I mean, think about it. If you crank up the tension, make it tighter, it's going to snap back faster, right? And if the string is lighter, less mass, it's easier to get moving. That's the physics. It has nothing to do with how fast you're shaking your hand or how big you make the waves. And remember, while that wave is zipping along the string, each little bit of the string is just bobbing up and down. That's simple harmonic motion. And for sound waves, it's a similar idea. The speed depends only on what it's traveling through, the medium. Is it air? Is it water? Is it steel? That's what sets the speed. And it just makes sense, right? Where the sound wave squishes the air molecules together the most, well, that's where you're going to have the most compression, and because of that, the highest pressure. So this is a big one, comparing standing waves. On a guitar string, it's fixed at both ends. The simplest wave you can make, the fundamental, has a wavelength that's twice as long as the string, and you get all the harmonics, the first, second, third, and so on. But with a pipe that's closed on one end, like a bottle, the physics changes. The rules are different. You get a totally different relationship for the fundamental, and you only get the odd harmonics, the first, third, fifth. It's a critical distinction to remember. And to finish up this section, beats and the Doppler effect. Beats are that classic wah-wah-wah sound you hear when two instruments are just a little out of tune. The frequency of that wah sound? It's just the simple difference between the two notes. And for the Doppler effect, here's the trick question to watch out for. If you and an ambulance are driving down the highway in the same direction at the exact same speed, you hear the siren at its true pitch. No change. Okay, let's switch gears to physical optics. We're basically taking everything we just talked about with waves and applying it all to light. This is the big mystery of this topic. I mean, think about how weird this is. You shine a simple laser through a tiny opening, and instead of just getting one spot on the wall, you get this wild pattern of bright and dark stripes. What on earth is causing that? Well, the answer is interference. Light is a wave, so different parts of the light wave can actually interfere with each other. But, and this is a huge but, to get a nice, stable pattern, the light has to be coherent. That's the key vocabulary word. All it really means is that the waves are all marching in perfect lockstep, like a team of synchronized swimmers. And here you can see the two possible outcomes. It's all about how the waves line up when they arrive at the screen. If two wave crests arrive at the same spot at the same time, boom, they add up. You get a bright spot. That happens when their travel distances differ by a whole number of wavelengths. But if a crest from one wave arrives with a trough from another, poof, they cancel each other out. You get a dark spot. And that happens when the path difference is a half wavelength off. Now let's talk about what happens with just a single slit. This is where your intuition might trick you. What happens if you make that slit narrower? You'd think the spot on the wall would get narrower too, right? Nope. The exact opposite happens. As the slit gets smaller, the main bright spot on the screen actually gets wider. It spreads out. It's a totally cool and counterintuitive result of light's wave nature. So the two big takeaways for diffraction are this. First, the effect is way more obvious for longer wavelengths. It's the reason you can hear someone talking around a corner, but you can't see them. Sound waves are long, so they bend easily. Light waves are tiny, so they don't. And second, the math for finding those dark spots is given by this simple formula right here. All right, let's do a quick fire round for fluids and thermodynamics. These topics might feel like they're from a while ago, but they are definitely fair game for the finals, so let's make sure these key ideas are fresh in your mind. First up, absolute pressure. Don't get tripped up by this. You know when you check your car's tire pressure and the gauge says like 32 psi? That's gauge pressure. It's the pressure above what the atmosphere is already pushing with. The real, absolute pressure is that 32 psi plus the air pressure from the atmosphere all around us.
Next, an adiabatic process. The key word to think of here is insulated. Just imagine a perfect thermos. No heat can get in and no heat can get out. Now, the temperature inside can still change if you do work on it, like if you shake it really hard, but there's absolutely zero heat exchanged with the outside. That's what true equals zero means. No heat transfer.
Okay, here's a classic exam question. We've been using mercury in barometers forever. Why? What's so special about it?
It's simple. Mercury is just ridiculously dense. And because it's so heavy, normal air pressure can only push up a pretty short column of it, about 76 centimeters. If you tried to build a barometer using water, you'd need a glass tube over 10 meters tall. Just not very practical.
And last but not least, please remember this. This is one of the most important ideas in thermodynamics. For an ideal gas, all of its internal energy, all that buzzing and bouncing of the molecules, depends on one thing and one thing only. It's temperature. Not the pressure, not the volume. If the temperature stays the same, the internal energy stays the same, period. Okay, let's wrap this up. How do we connect all these different topics into a few big overarching ideas? This table really boils it all down. For waves, just remember, the medium is king. Its properties set the speed. For interference, it's all about the path difference. Do the waves arrive in sync or out of sync? For diffraction, it's a showdown between the wavelength and the size of the opening. And for resonance, the boundaries, the ends of the string, the shape of the pipe, they dictate everything. If you can explain these 4 core principles, you are in excellent shape. Look, you've been working hard all semester. You know this stuff. The concepts are there. Just go in there, take a deep breath, and show them what you've learned. You've got this. Good luck on your final AUB.